Awesome. Okay. So let's talk now about how expectation is related to independence, which we discussed last week. First thing to notice is that if you condition on an independent random variable, the expectation doesn't change. So let's just remember what the heck is independence in the first place. If x is independent of y, we know that the probability of x given y is just the same as the probability of x. So the conditional probability and the marginal are the same. Knowing y doesn't give us any more information about x. So this actually transfers over to the conditional expectation as well. Because if knowing y doesn't tell us anything about any part of x, it's sure as hell not going to tell us about the mean of x or any other specific part of x, right? So you can see this in a kind of brute force way if you write out the definitions here of this conditional expectation. You can write it as a sum over the conditional density times the value that x takes here. And the independence says that this conditional density is the same as the marginal density if they are independent. And so now we see that this is just the definition of the expectation, the marginal expectation. We also can see the same thing happen if two variables are conditional. If two variables are independent, conditional on a third variable. So in this case, x and y are independent, conditional on z. So in this case, I'm asking about the subpopulation average of x in a stratum defined by x, y, and z. But I know that the distribution of x does not change depending on what stratum of y I'm in if I already know that I'm in a particular stratum of z. And so that can just drop out. And again, mechanically, if you want to see that you can kind of follow this exact same process, you just have this extra conditioning held through. And then from here to here, you have to use the definition of conditional independence to equate those densities. And lastly, you can use this to show that the expectation of a product of two random variables, again, think of this as like a derived variable. If you have two variables in your population data set, x and y, x times y is a third variable. You've done like a mutate in that data frame. And if you want to know, well, what's the mean of that thing? It turns out that if x and y are independent, only if they're independent, there may be some special cases where this can work if they're not, but if they are independent, you can say for sure that the expected value of the product is the same as the product of the expectations. And so here let's work out why that happens. I'll give you a hint here. So you can use total expectation and then pull out some constants basically. So I do encourage you to try it first. And here's the kind of steps. So first, use total expectation and linearity to find this. So convince yourself that that's true. So we've gone from here to here. And now you want to go from here to here using independence and linearity. So try to convince yourself of this and do it in a little bit more detail. Okay. So let's try this. By total expectation, we have this. Okay. And here, to remind yourself, here I'm like averaging over the little y. That's over the values, the density that little y has in the population. Or you may also see this just written like this, because that little y is kind of unspecified. So I've just conditioned on the value of y. And now this next step is kind of stupid because in here, if I already know what y is, then the value of y here is just a constant. So again, if I were to write it how I had it before, so let's just pull this out so that you can make this concrete. So xy given y is equal to little y. If I already know that y is little y, there's no point in having big Y here. I can just write this as expected value of x times little y, given that y is equal to y. Okay. And now, since this is just a constant, I can use linearity of expectation to pull that out of the expectation. And I have this. Now remember, that's just the part that was on the inside. Now I have to average over all of that. And while I was writing this, I was saying y is equal to some constant. But now, as it pertains to the outer expectation, I need to average over what that is. So I have big Y here, and that is this first step. So we're done here. Okay, step 2, independence and linearity to find this result here. Okay. Well, because of independence, this thing here you should recognize is just the expected value of x. Okay, so the conditioning on y doesn't change it because they're independent. We just saw that. And so now what we have is expected value of y times expected value of x, like that. And now we use linearity again to pull this guy out, because this is just some number, like 10, 5, minus 3, whatever that is. That's just a number. So we can pull that out, and then we have finally our result. So the tricky part, I think, for me, is here. This is mechanical. This from here to here is kind of mechanical. It's kind of in like when you're considering this inside expectation, you have y equal fixed at some particular value. But then when you go to the outer expectation, you realize that you're actually averaging over what that value is. And you may be able to see that a little more closely if you look at if you write these expectations in terms of like the sums over the densities. Things will be a little bit clearer. But notationally, this is the way that you will see it in the textbooks. So here's a related result. Here we showed that expectation factors if the random variables are independent. And then here it's the exact same thing. It's just that you can, if they're not independent, if x and y are not independent, but they are conditionally independent given z, you can factor them into this, the product of the conditional expectations. Okay, so here's a data generating process. And without doing any computation or anything, can you tell me what the mean of z is? So this should be pretty quick. Just looking at this, you should know that this has expectation 0. It's right there. This one, again, just looking at it, it's a random number between -1 and 1. Expectation is 0. Therefore, linearity of expectation here, expected value of z is 10 times expected value of x plus expected value of y. That's 10 times 0 plus 0. So marginal expectation, also 0. What is the expected value of the product of x and y? So again, this is very straightforward because in this data generating process, you should recognize immediately that these two are marginally independent. And you can see that if that's not totally obvious immediately, you can see that by drawing the DAG. So you just say, okay, does x have any variables going into it? No. Y, does y have any variables going into it? No. Z, does z have any variables going into it? Yes, x and y. Okay, so it looks like this. And then you can play the D-separation game, where if I want to know are x and y marginally independent, let's draw a path between them. Oh, but actually that path is blocked because z is a collider. So indeed, they are independent. But after you do this once or twice, you'll you'll just immediately recognize in a data joining process like this that certain variables are marginally independent or even sometimes conditionally independent without even playing this game. So from that, we now know that this factors, and we know this is 0, we know this is 0, right? So then that product is 0.